Hey everybody, and welcome back to Linear Algebra Online. So I just want to start off and kind of show you why, one of the reasons, there's many reasons why we'd want to diagonalize a matrix, but one of the things that's definitely easier given a diagonal matrix, and that is powers. So these are the kind of things too that like the back end of like Python and a lot of these things, they have tricks built in to handle like things like a lot quicker. Like instead of doing this matrix to the 10th, they might do checks to see that, okay, we can diagonalize it. And then there's like, we're going to do this to the 10th because it's much easier. So this is a matrix that we actually can diagonalize. A has, basically these are going to be the eigenvalues with a sign change, really. So we have, you'll have lambda 1 equals, you'll get negative 1. You can get these off your calculator too. Lambda 2 is 2. And then the eigenvectors, okay, are 1, negative 1, and for this one you should get 1, 2. So you can do it. Trust me. I mostly want to show you the benefit of basically doing instead of this to the 10th, this to the 10th. So and I'm basically just using this, okay? Like if A is similar to a diagonal matrix D, then powers are also similar, right? So what this means is that I basically have, A to the 10th is going to equal P D to the 10th times P inverse, right? And so then you can just go, you can create the matrix 1, negative 1, 1, 2, right? Your matrix built out of eigenvectors. And then D is the eigenvalues. And here I can just do those zeros. We're going to raise that to the 10th. And then P inverse, if you do that on your calculator, you get 2/3, 1/3, negative 1/3, and 1/3. And the nice thing is that when you do this, just copy all this down. The part where it really gets easier is that if you do a diagonal matrix to the 10th, or to any power, say, it's equivalent to just doing each entry on the diagonal to that power, which is computationally way easier than having to deal with like literally this times another one times another one times another one. And these are the things that like we really need to figure out ways to build into like our algorithms for a lot of computer programming, because it's going to speed up tons and tons of stuff on the back end, and then allow you to do harder and harder computations. So there's a whole field of kind of math and computer science stuff where you do like algorithm design and you like try to create the most efficient way to do something. And this is one example. That's like a really efficient way. So that is a much easier thing to do. And I would argue that like to the 10th, I bet you your calculators and all, I honestly haven't tested it, but you could easily do this to the 10th. But the problem is going to become really tough when this gets to be like 1,000 or something like that. And this to the 1,000 is really easy. You can absolutely do negative 1 to the 1,000, 2 to the 1,000, and then just do 3 multiplications. I guess 2 multiplications, right? Of matrices. So just so you know, this is what it equals. But you get 342, 682, 341, 683. So that is equal to A to the 10th, but we've done it through like a different way. It's a cool little trick. All right, so what I really want to talk about today is just conditions for diagonalization. So we want to know like when can we even do it? And one of these in particular is really kind of the one that I use the most, I would say. So all of these can be used though. So if you have an n by n matrix with n distinct eigenvalues, then A is going to be diagonalizable. So basically if you have 3 by 3 and you get like eigenvalues of 1, 2, 3, like 3 different ones, that will always yield something that you can diagonalize, because basically there's going to be a corresponding vector for each one of those. And so then you can be able to build the matrix P out of that, and all that stuff. So that's one thing. That's kind of like your nicest case. A lot, you might get just like literally n distinct eigenvalues for n by n, and then it's diagonalizable. These other cases, though, so these are all equivalent statements, and so the way I kind of read this is that if I can find that B happens, then I get that it's diagonalizable. And if I can find that C happens, I get that it's diagonalizable. And what I remember doing the most in my higher level math classes was I was trying to get something to be diagonalizable. And so what I would do is I'd be checking, and this is the one that for me it was easiest to check. So this one, I'm not going to say too much about it. It's pretty intuitive if you read it, but this is the one that today I really want to talk about, and I'll show you a few examples of how I use it to check if something is diagonalizable. But this is an equivalence theorem, so you could also just, if it's diagonalizable, then you know that the union B of bases for the eigenspaces of A contains n vectors. And if it's diagonalizable, then the algebraic multiplicity of each eigenvalue is equal to its geometric multiplicity. And so everything here, and I didn't really mention this in the last video, and I meant to, but there's like a space issue with diagonalization. So the idea is like if you're trying to construct this matrix P out of the eigenvectors, right? And you have a eigenvalue that has is a repeated root, but the eigenvector, gosh, I'm having a hard time with my words here. The eigenvector for that is not repeated, it's just one vector. That can happen, right? Then there's a space issue in creating P. You need P to be n by n, but it would not be because you don't have enough vectors to make it and build it up with all the columns, right? And that's why this test becomes so important. So algebraic multiplicity, again, is just like the algebra 2 stuff. You can have x to the, 10th or whatever, which is right, just like x and then times x times x, 10 times. And that just means you have a root of 0 10 times. That is multiplicity, algebraic multiplicity of 10. Geometric, though, is the dimension of the eigenspace. So you might have an eigenspace for, say you have something like lambda 1 equals lambda 2 equals 3 or whatever. It's very possible that, the eigenspace is not two-dimensional, that the eigenspace might just be the stuff on this line right there or something in 3D space or whatever. If you have that situation, then this is saying that you're not going to be able to diagonalize. So maybe I should write that. Given this, basically whatever matrix we have A is not diagonalizable. And I'm going to show you examples of this kind of idea. So, the idea is then you wouldn't have the space to build up P, right? Because you need, if you have repeated root, right, you need to have a plane's worth of eigenspace, right? You need to basically have some sort of plane there, and you have two direction vectors for that plane, right? Here and, here or whatever. And these things, these vectors are what you're going to pop in for P in the, for this eigenvalue. And then maybe you have another eigenvalue or something that, could create the last column for a 3x3 or something like that. But this is a very quick and easy thing to check, especially if you're using a computer to help you get eigenvalues and eigenvectors. So let's do that. So this is, we did that last time. I don't need to do that again. I was just I put this in here just to kind of remind you quick of what we're doing. And I meant to kind of put this earlier before I started talking about this, but what we're doing again with P, right, is that we're creating P out of the columns are its eigenvectors. And so if you don't have enough eigenvectors to create P, you're not even going to be able to do this whole P inverse AP thing. So that is why this last statement is so important. You need that geometric multiplicity to be equal to the algebraic one in order to get diagonalizable. And I guess it's worth noting too, so geometric multiplicity would always have to be less than or equal to the algebraic multiplicity. Right? You could never have, if you think about the computation of how you're getting eigenvectors, you can't get like a three-dimensional eigenspace for a repeated like double root eigenvalue, right? So what we could get is definitely dimension down, like I was talking about here. We can get a linear eigenspace for a repeated double root thing. But we could never get a three-dimensional eigenspace for a repeated double root, right? It just wouldn't make sense based on how you compute this thing. But anyways, so this is kind of what I remember doing a ton of in my higher level classes. So I would have some sort of matrix. I would want to diagonalize it for tons of different reasons that we don't have a ton of time to get into, and you'll learn about more in courses down the road. And so this is kind of what I would do. I would find my eigenvalues, and in this one, I would use a computer or something. I get lambda 1 equals lambda 2 equals -2. And then I also get that lambda 3 is 5, right? And what I would notice is, this one right here, whoops, sorry about that. This one right here has algebraic multiplicity 2. So I need, right? So in order to diagonalize, I need the geometric multiplicity of the eigenspace for lambda, like 1 and 2, we'll call it that, to be 2. Okay, I need a plane's worth of eigenvectors, basically. And what you would notice, okay, if you go and compute the eigenvectors, okay, you're going to get 1, 0, 1 as an eigenvector for lambda 1 equal to lambda 2 equal to -2. And you get only that. You don't get another one, okay? And so, like, if you go and try and construct P, right, you're going to start popping in vectors. You're going to put in your 1, 0, 1. You actually get another vector of 8, 0, 1, okay? But then you would be done. And you would have, like, this weird column. This is what I mean by a space issue. You would have a column where you can't basically put anything in. There's no more vectors to put in. And so you would not be able to diagonalize it, okay? And so this is a case where the geometric multiplicity of this space, the dimension of the eigenspace for this eigenvalue, is 1. 1 is not 2. And so you can't diagonalize this thing. So this final answer to this question is, since 1 doesn't equal 2, you can't diagonalize. And that's it. And that's probably, to me, always been the easiest way to check these things, since so much of it is just checked, like with a computer, finding eigenvalues and eigenvectors already. It's just quick, okay? Here's another one. Just want to do the same kind of thing. So I'm going to start and write down all my eigenvalues and corresponding eigenvectors. All right, so this is one where actually, since we're getting we're getting two distinct eigenvalues for a 2 by 2, that's actually enough to know that we could diagonalize it. That goes back to this one, right? So we've basically satisfied that first condition, and so then we know it's diagonalizable. And then I think it's good to just do the process of showing this just again. So to diagonalize it, we basically need to build P out of these eigenvectors. Okay, so P is going to equal 3, 4, negative 1, 1, negative 1, 1. And P inverse would equal, all right, so if you just do, what do I want to do here? I want to do P inverse AP. Okay, now we got all the stuff we need. If we multiply that out, we would get, this diagonal matrix 5, 0, 0, negative 2. Okay, and then again, like in the real world, what's going to be nice is you're going to be able to, like, a lot of things that you would want to do with this matrix A are now going to be done with this much easier matrix D, right? So that is, to me, always been the easiest way to check this kind of stuff. It's a very important thing to know when you can and cannot do it. All right, just one more kind of thing. So this is actually kind of going back to the first problem sort of again. So we saw before, like, how we can raise something to the 10th, but we could even get a formula out of this if you can diagonalize something, right? And this is another one that you actually can diagonalize. So if you think about that first problem that I did, right? You basically, if you can diagonalize, right? If this is my matrix like A, right? So A to the kth, right, power would equal P D to the k, P inverse, right? And so basically, if you can diagonalize something, you can also get like a formula for the power of it. And so here, I got to get all my eigenvalues and eigenvectors, which are these. All right, so eigenvalues, corresponding eigenvectors, then that would mean that P is like 1, 1, negative 3, 1. And then if you just do P inverse on your calculator, you'll get 1/4, negative 1/4, 3/4, 1/4. All right. And then, we know that D is going to be 3, 0, 0, negative 1. And so a formula for this thing, right, could literally just be, so A to the k power is going to equal 1, 1, negative 3, 1 times 3 to the k, 0, 0, negative 1 to the k, and then 1/4, negative 1/4, 3/4, 1/4. Right? And now you can just go and literally, like, do out the matrix multiplication. You can multiply these and then multiply the result by this, and that is way easier than trying to, like, figure out some k power of that thing. And this is just a nice byproduct of, again, this being such an easy thing to do. You don't have messy, this would even be the case too, even if every single term here was a new number besides 0. Like, that 0 makes it a little bit easier, but it is much easier even still here with having 2 zeros versus 1 0. So just as a final answer, this is what you get. All right, so this is what you get. 3 to the, that's a k, plus 3 times negative 1 to the k over 4. This is 3 to the k minus negative 1 to the k over 4. And then 3 to the k plus 1 minus 3 times negative 1 to the k over 4. And then 3 to the k plus 1 plus negative 1 to the k over 4. So this is now, like, just a super easy thing that if you wanted to know a power of this, you now have a formula, and you can just literally, like, okay, I want the 22nd power for some reason, and you just pop in that, and it's so easy to put in, powers of the numbers versus powers of a matrix now. So just kind of a cool trick to see. Kind of a generalization of the first problem, but again, definitely assumes that you can diagonalize the matrix.